Hello everyone, and now let's continue to discuss the design of short columns here. Here we would like to understand why we have unsymmetrical columns. Look at this. This is a symmetrical columns, whereas one you see here is not symmetric. Why is that? That's because of your lebar, which is installed symmetrically or unsymmetrically. If your lebar is installed symmetrically, then your PM diagram will be also symmetric. Otherwise, your PM diagram will be tilted. Okay, the reason for diagram is tilted. A uniform compressive strain of 0.03 cross the sections, corresponding to the maximum actual load capacity leads to a moment, since the forces in two layers of the steel are unequal. Do you understand? Okay, if the lebars on both sides are not symmetrical, or is not equal or unequal, that meaning all same things, then your PM diagrams, they're representing the maximum actual load capacity and the moment capacity will be tilted. Okay, this is the way you can take a look at and you guess the shape of your PM diagrams. Alright, here we're gonna review the PM diagrams that we learned so far, and we have a 5-point 1, 2, 3, 4, 5, and there's another point here in the other side of the x-axis where we have the point, the uniform tensile strain of -1 in the steel with the concrete cracked. So when you have a strains which is tensile, then your concrete is very weak, vulnerable with the tensile strengths in the section. So when you have a minus epsilon y where you have a tensile section on the columns, then your column will be immediately cracked, and this point indicates that point. And this is the other way. We have a concrete section, entire concrete section corresponds to 0.03 pure actual force. Here we have a uniform tensile strain of minus epsilon y in the steel, so that concrete section will crack. So we will never see this point in PM diagram that we use for design practice. And here this point, do you understand what this point means? A design diagram, strain diagram corresponding to a incipient cracking, onset of cracking, passing through a compressive strain of 0.03 on one face and zero strain on the other. Zero strain on the other means we don't have any tension strain developed yet. It's about to develop a tension strain on the other side of the section. Okay, again, this point will represent this point where you have a 0.03 of concrete strain, where you have zero tension on the other side of the section. So you mean on the other means the other side of the section right here, which indicates tensile side of the columns. And here again we have a 0.03 which don't change it, but in this size of tension will reach a epsilon y, which is yielding strain for the bar. If you remember, the balanced strain distribution and limiting compression control the strain distributions, both of which have compressive strain of 0.03 on one face and a tensile strain of epsilon y at the centroid of the tensile steel, which means that the tension steel at the end of the section of the column will reach epsilon y. Okay, so here if we have here the bar here, here we have rebars, for example, and this will reach strain. This one is epsilon y. Okay, so you're having a, okay, let me plot this way. You're having a epsilon y for rebar tension, and then you go epsilon c for concrete. So this value don't change at all. Okay, so this is what that happened here, right here, and here is where we have a tensile strength of 0.05, if you remember. Okay, so limiting tension controlled strain distribution having a compressive strain again 0.03, don't change it on one face, and tensile strain reaches 0.05, and the reinforcement layer nearest to the tensile force. Okay, and here at this point we don't have any axial load. This is what we learned to construct a PM diagrams. Now let's go and wrap up some of the factors, important things about design of short columns. And here we have three cases of columns where we have a different lever layers. If you take a look at, let's assume that we have used a rebars which is similar in all cases, three cases where we have just two curtains of lever layers. That means we can go further here, right? You can go further here. And we have a four-sided of lebar, and we have a circular lebars. If we go further in this side, okay, we can go further in this side, or many lebars in this side, because we have only two sides, so that we have a better moment resisting capacity for this case, like this. Okay, this is very good. So let's say this is M1, and say this is M2. Moment capacity, this is M2. And this is moment capacity, this is M3. So the M1, M2, M3, they are having a proper or appropriate eccentricity ratio to apply. If you have two layers of rebars, they can be more effective in resisting moment for big eccentricities. Here, eccentricity, E over H can be 20%. What is E? Eccentricity, if you remember, eccentricity. Okay, this is its eccentricity. This is its eccentricity, and this is H. So H, E over H ratio is the ratio that how effectively can you resist moment. So if this is 0.2, which means that this is 20% of entire depth of the columns. Okay, this ratio is good to know. How big it is or how small it is when you design your columns. So here, when you have two layers of rebars, so you can distribute rebars as far as horizontally, because you have only two layers, then this column is good for a large eccentricities over 20%. Whereas you have here the circular thing. Circular, we have rebars here, rebars here is very limited. You can't go that far because you have to go back, right? So your rebars is concentrated. I should say concentrate with respect to neutral axis here. Concentrate with respect to neutral axis. So that means that your circle column is not very effective to resist a loading with a big, large eccentricity. So your eccentricity ratio is very limited, less than 10%. And if you have a four-sided rebar ratio, then your column will provide a considerable good eccentricity ratio. So I will say that this eccentricity ratio, that this column with the four layers can be between these two cases. So that it's going to be between this and this, which is around 20% or less. Okay, so your eccentricity ratio represents how effectively you can resist moments. It depends on how you lay out your rebars. Okay, so you're laying out rebar with respect to neutral axis, and you are concentrating your rebar with respect to neutral axis, then your eccentricity ratio that your column can resist is very limited. Otherwise, you have to distribute your rebar as far as from the neutral axis, right? So that you can have a better capacity to resist your eccentricity ratio right here. Do you understand what I'm saying? Okay, so that for seismic areas, you need a big eccentricity ratio for columns. Okay, so here for seismic design, you may need a rebars in four faces to be able to resist the moment about both axes, X and Y axis. So you must use this for seismic actions, but in two phases it's not very useful. Even if you can increase the depth of perpendicular to the axis by using a rectangular columns, that means even if you can locate your rebar from the neutral axis as far as from the neutral axis to get a good eccentricity ratio, but this column it's not going to be well used for seismic area because this moment it's not going to be very good at two axes. It's good about one axis. So this column is not adapted for seismic designs. And here, whereas we have a spiral columns, the phi factor is 0.7 and 65. And also this spiral column is very expensive because this is very expensive to form a spiral hoops. You know that spiral hoops. This is expensive, so that these ties are expensive. But there's a lot of architects love to use a spiral columns or circular columns because they're looking good in some cases for the aesthetic point of the design. What is aesthetic? Okay, aesthetic means 신미안적인, 미적인. So the architect love the circular column for aesthetic reasons, but this is expensive, as you know. And do you understand how we can use and install rebars for these three cases? Okay. 그러니까 여기에 있는 경우는요. 여기에 있는 경우는 같은 양의 철근을 사용하지만 쭉 옆으로 보낼 수 있으니까 이렇게 옆으로 보낼 수 있으니까 중립축에서 멀리 리바를 설치할 수가 있겠죠. 그렇죠? 그렇기 때문에 이제 이 편심이 많이 걸리는데 유리하다 이런 얘기죠. 이렇게 근데 이제 4개를 쓰면은 내면에 보내면은 중립축에서 이렇게 멀리 보낼 수는 없지만은 두 방향의 모멘트를 우리가 견딜 수 있죠. 어쨌든 간에 중립축에서 멀리 보낼 수가 없기 때문에 이제 이런 경우에는 이제 또 이센트리시티 편심이 좀 제한되죠. 칼럼이 기둥이 지탱할 수 있는 편심 마찬가지죠. 원형도요. 이런 경우에도 이건 더 작죠. 10%, 20% 이하. 이건 20% 이상까지 간다. 이런 뜻이죠. 예. And now we're talking about the reinforcement ratio in the column. So what is the reinforcement ratio as we learned previous lecture? It is a lever over a gross area. This is called a reinforcement ratios, and the reinforcement ratio, minimum reinforcement ratio of the column is recommended as a 0.201, which is 1%, where the maximum ratio can reach 8%, but it's gonna be limited to 6% in seismic regions. Why is that? So we need if you have too many rebars, then it may not be very ductile, because the rebar cannot yield when you have too many rebars. So for seismic regions, in order for designing a ductile columns, we may limit the rebar ratio to 6%. But non-seismic area we need, and we can go to 8%. But the minimum ratio is both cases, seismic and non-seismic, is 1%. And we also have a minimum number of reinforcement in the columns. For rectangular columns, we need at least 4 rebars on the column when you have a rectangular columns. When you have a circular or spiral columns, you need 6. 1, 2, 3, 4, 5, 6. So this is a sort of minimum number of reinforcement in columns. Let's take a look at one important thing is the most economical tight column sections generally designs for the rebar ratio of 1 to 2%. Even though we are allowed to go to 6%, 8% right there, the most economical tight column section will be 1% and 2% of the gross section of the columns. As a result, tight columns seldom have a rebar ratio greater than 3%, which means that the most economical section we will design 1 to 2%. 굉장히 경제적인 설계를 위해서요, 우리가 기둥에 들어가는 리바 레이셔는 1에서 2% 정도 이렇게 사용한다, 이 얘기죠. 그리고 3% 이상 되는 경우는 이제 별로 없다, 이런 얘기입니다. We have a fire code. We need to resist fire for some period of times. For example, if we need to resist 1 hour against the fire, then we need at least minimum column thickness and minimum clear cover. So we need a column thickness at least 225 millimeter with 25 millimeter of clear cover. Clear cover means the distance from rebar to the outside of the section. This is called the cover. Okay. And if you need to resist 2 and 3 hours against the fire, we need at least the minimum column thickness of 300 millimeter with a 50 millimeter cover. And also the minimum column size. We have some limit in column size where we have tight columns. The minimum dimensions should be 200 millimeter or 20 centimeter, preferably not less than 250 millimeter. It's too small, you mean 200 millimeter. And spiral columns, we have a minimum dimensions, diameters 300 millimeters. So that we recommend to use a minimum 250 millimeter for the tight columns, 300 millimeter for spiral columns. Okay, this is a regulation for Korean design code factors affecting the choice of columns here. And again, the main lever, the vertical lever, and hoop, and it includes hoops. And we're gonna use a 400, 600, depending on the diameter of the levers. If you're using a diameter 13 millimeter, then you have to use 400, and 16 millimeter you can go up to 600 megapascal. And if you now the stirrups, the yield strength went up pretty much, so you can use 500 megapascal for stirrups and hoops, and you can still go up to 700 megapascals for the spiral columns, and this is pretty good. So that it's good to use a higher strength for strength designs, and this is our same for Koreans and ACI American code 0.01 and 0.08. The maximum rebar ratio is small. I mean the minimum rebar ratios, and if we have a splices, then the maximum rebar ratio cannot go over 4%. But in any case, as we explained, this is what we recommend, right? 1 to 2%. Okay, and also the number of rebars that we use in rectangulars 4, and the spirals 8, and if you are using a triangle hoops, then 3. Triangle hoops is 3 that we can see 1 here, 1 here, 1 here. Right? If we have a columns, we can use a spiral, something like that. 1 here, 1 here, 1 here. But I never seen this column, so I don't know. This is not very usual, but this is usual. This is common. Okay. This is a PM diagrams that design code provides properties of interaction diagrams for RC columns. RC columns here. And x-axis represents moment, as we know. Y-axis represents actual force, but x-axis is normalized by BH square. BH square. So this is B, column width, and this is H, and where we have moment this way. Right? So that the x-axis is normalized by BH square, means that x-axis divide the design moment by the BH square, whereas y-axis we normalize the actual force by BH, which means that we divide the actual capacity by BH, and we have here both axes, no dimensions, so we just decimal numbers right there and integer numbers right there. Okay, so what we do, we use this PM diagrams and designing columns, and we'll take a look at how we can use this PM diagram to design column. 자, 이 그림을 한번 볼까요? 우리가 배운 거를 한번 여기서 찾아보면요. 여기가 뭐였죠? 여기가 순수 축구 강도를 지정하는 부분이죠. 그리고 이 윗부분을 우리가 뭐라 그랬죠? 예, compression controlled region이라 그랬죠. 그래서 이제 여기까지 이렇게 내려오고요. 그 다음에 여기가 이제 tension controlled region이라 그랬죠. 그죠? 이 사이는 뭐라 그랬습니까? 여기는 이제 transition region이라 그랬죠. 그죠? transition region. So we have here the pure axial regions right here, where there's no moment is acting, and we have a compression region all the way up to down to this point, and we have another region for tension control. In between we have a transition regions here. So for compression regions, which means that we are able to resist a small eccentricity, because the compression means we do not have a big eccentricity. This is eccentricity from here to here. Alright. So for compression controlled region, we have this eccentricity is small. So we are looking at here 20%, 30%, 40, 50, so that when you go down there towards the tension control region, we know that eccentricity increases. Okay. So this is what we have to see from PM diagram in any types of PM diagrams, and here the eccentricity is about to be the same as the column depth, which is h. Alright, so this is pretty big eccentricity, can be resisted in tension region. This is easy to understand. If you have very big eccentricity, E, and your actual load, then you are having a very big moments. So you turn your columns over. Alright. So very big moment with a very big eccentricity will turn your columns over. So that you need a tensile strength occurs right there. And this is compression, which is 0.003, and you have a tensile strength right there. So let me just draw a big section here. So you have a big moment with a big eccentricities, then you will have a big strain, and this epsilon c, which is 0.003, and this is epsilon s. Epsilon s can be equal to and bigger than 0.005 and more. So that is why we call this a tensile control regions. 자, 그래서 우리가 여기를 텐션 컨트롤 리전이라고 부르는 거예요. 그렇죠? 왜냐하면 여기는 지금 편심, 굉장히 큰 편심이 작용하는 지점이죠. 얘처럼. 그렇죠? 그래서 이 편심이 이 중립축에서 기둥 중심에서 이 편심이 굉장히 크죠. 이렇게. 굉장히 큰 편심이 작용하는 기둥에 대해서는 다시 한번 설명합니다. 모멘트가 굉장히 크게 걸릴 것이고, 모멘트가 굉장히 크게 걸리면은 이제 따라서 텐션이 지배하는 영역의 설계가 돼야 되겠죠. 반면에 이제 일로 올라와 버리면은 이제 편심이 점점 작아지죠. 또 반대로 올라갈수록, 그죠? 그래서 이게 아주 PM 다이어그램의 특징이다, 이렇게 보시면 되겠습니다. 그래서 이제 이건 또 뭐냐면은 이제 철근비예요. 철근비가 1%일 때, 2%일 때, 3%일 때 이게 이제 뭐 8%까지 갈 수 있죠. 8%까지 갈 수가 있는데, 철근이 작으면 아무래도 PM 상관도의 이 면적이 작아지겠죠. 이 안에가 면적이죠. 작아지겠죠. 또 크면은 커지고. 그런데 우리가 설계할 때, 프랙티컬 설계할 때 말이죠. 2% 이상은 넘지 않으면 좋겠다 그랬어요. 그래서 우리가 대부분의 설계는 이 안에서 이제 이루어지는데요. 이렇게요. 이 안에서 이렇게 이루어지는데, 그죠? 이 안에서 이루어지는데, 실제적으로 이 구조물에 가해지는 모멘트하고 충력이 이 밖에 있으면은 이 설계는 bad 설계가 되는 거죠. So 우리가 그걸 모멘트, 소요 모멘트다, 이렇게 얘기합니다. 소요 모멘트는요, 반드시 표기할 때 MU로 표기합니다. MU. 그렇죠? 그래서 MU를 구할 때는 우리가 팩터를 집어넣죠? 배웠죠? RC1에서. 그래서 사 중에는 뭐 예를 들어서 1.2, 뭐 화라 중에는 1.6, MD, ML 이런 식으로 다 배웠죠. 그죠? 그래서 하중에는 1 이상을 곱해지죠. 왜냐하면 안전하니까 그게. 하중으로 1.0만 설계하면 뭔지 모르게 좀 마음에 안 놓을 수가 있기 때문에 하중을 계산할 때는 어떻게 한다고요? 예. 항상 1보다 큰 팩터를 곱하죠. 우리가 그걸 뭐라고 그러냐면은 로드 팩터라고 합니다. 로드 팩터는 1보다가 큰 숫자죠. 그래서 우리 기준에서는 어떻게 하냐면은 1.2 예를 들어서 데드로드에 대해서는 1.2, 라이브 로드, 화라중에 대해서는 1.6을 곱해서 우리가 소요 하중을 계산하는 거죠. So we call 소요 하중을 we call the moment demand. So moment demand also is called a factored moment. Factored moment. I guess we all learn from RC1. Very well. RC1. Okay. So we call moment demand or factored moment. So factored moment includes a load factor which is greater than 1. Why? Make sure that we are having a safe design. So we increase the load. Right? Whereas we decrease what? We decrease the capacity. Amen. Amen. And we have to multiply phi factor. Right? What is phi factor? Again, this is the review. Phi factor is strength reduction factor. reduction factor. 그래서 우리가 모멘트 능력에는요, 우리가 이걸 다 사용하면 또 좀 불안하죠? 그래서 우리가 우리의 모멘트 능력은 또 줄입니다. 리덕션 시킵니다. 그렇죠? So we call this strength reduction factor. 그래서 하중은 크게 해서 사용을 하고, 그렇죠? 모멘트 능력에는, 단면 능력에는 줄여서 사용을 하고, 이렇게, 그죠? 얘는 늘려서 사용을 하고. 그러니까 안전핀이 이제 이중으로 있는 거죠. 그죠? 이렇게. 그래서 결론은 어떤 식을 우리가 배웠냐면요. RC1에서 이런 식을 배웠죠. RC1에서 뭘 배웠냐면은 MU factored죠. 늘려놓은 MU. 그죠? 늘려놓은 MU는 줄여놓은 phi factor의 MN보다가 더 작아야 되겠다. 이게 굉장히 중요한 설계식이죠. 여기서 우리가 phi factor가 붙은 MN을 우리가 뭐라고 부르냐면요. 설계라는 말을 붙여요. 설계 모멘트 강도. 이렇게. 이게 충력이면은 phi MN이면은 설계 충력. 또 전단이면은 설계 전단 강도. 뭐 이렇게 부르죠. 설계라는 말을 붙이죠. 설계라는 말이 들어간다는 얘기는 우리가 phi factor를 곱해줬다. 이렇게 보시면 되겠습니다. phi factor 곱해있다. 이렇게 보시면 되겠습니다. phi factor가 곱해있다. 이렇게. 만일에 phi factor가 없는 경우는 뭐죠? 우리가 phi factor가 없는 MN은 뭐라고 부릅니까? 그렇죠. 공칭이란 말을 붙이죠. 설계가 아니고 공칭 모멘트. 공칭이라면 이제 일반적으로 just 모멘트 강도란 얘기죠. 아무것도 안 붙었다 그런 얘기입니다. 공칭이란 말은 공칭 충력 이렇게 또 말할 수 있고요. 공칭 전단력 강도 이렇게도 말할 수 있죠. 그래서 설계할 때는 우리는 공칭을 쓰지 않는다. 설계할 땐 뭘 쓴다고요? 설계 모멘트 강도를 쓴다. 설계 모멘트 강도는 phi가 붙어 있는 거다. 자, 절대 잊어서는 안 되겠습니다. 절대 잊어서는 안 되겠습니다. 한번 복습을 해봤고요. 굉장히 중요한 개념이기 때문에요. 다시 또 기둥 PM 상관도로 돌아가서 정리를 한번 해보겠습니다. 그래서 우리가 문제에서 주어지는 이제 하중을 구하죠. 하중은 이제 두 가지로 나오죠. 충력과 모멘트. 이 충력과 모멘트로부터 우리가 MU를 구하죠. We calculate factored moment and factored actual force so that we know these two values, and these two values must be located inside of the PM diagram that we are looking at, right? So if the MU and PU is here, then we have to use this PM diagram for design. This PM diagram for design. Okay. So if your MU and PU is here, then we have to use this PM diagram for design. So this PM diagrams will help you design RC columns against MU and PU. MU and PU is again the moment demand and actual force demand, or factored moment and factored actual force. Do you understand? So make sure that one more time. MU PU is less than VMN VPN. So here we say nominal, and we multiply V factor to make nominal to design moment and design actual. And MU and PU, it's called a factor the moment, factor the actual force. Don't forget this. I may ask you this definition in exam. Definition. Okay. You get this question right if I give you one in the exams. Let's solve a example problems to see how we can use the PM diagrams to design a columns. And problem says that design a rectangular reinforced concrete column for following conditions. The column has unsupported height of 2.2 meters and is braced against sideway. Architectural considerations limit the width of the column is 400 millimeter. Moments are negligible about the weak axis. Okay. So 이 문제를 잘 한번 이해를 해보겠습니다. 첫째, 이제 칼럼 높이가 2.2m죠. 2.2m. 2.2m하고 브레이스가 잘 돼 있다 이런 뜻이죠. 다시 말하면 칼럼은 지금 이렇게 캔틸레버처럼 움직이지 않는다 그런 뜻이에요. 이렇게 캔틸레버처럼 움직이지는 않는다. 무슨 얘기냐면은 칼럼 위아래가 이렇게 보로, 그죠? 우리가 프레임을 보면은 이렇게 잘 구성이 되어 있잖아요. 이 칼럼 하나를 떼어내서 보면은 이렇게 되어 있죠. 그죠? 그래서 얘는 캔틸레버처럼 움직일 수는 없죠. 움직인다 그러면은 이제 뭐 이렇게 움직이겠죠. 그죠? 그래서 캔틸레버 쪽처럼 움직일 수는 없다. 그런 뜻입니다. 캔틸레버처럼 움직일 수는 없다. 이런 뜻이 되겠습니다. 자, 왜 이런 조건이 붙냐면은 이런 조건 하에서 만들어진 PM 다이어그램이기 때문에 그렇습니다. 이런 조건 하에서 만들어진 PM 다이어그램이기 때문에 그렇습니다. 그래서 여기에 만약에 이제 이렇게 브레이스가 잘 안 돼 있어. 브레이스 하면은 뭐 우리가 이제 단단히 잡아매는 걸 말하는 거죠. 브레이스가 잘 안 돼 있는 경우에는 이제 12장에서 배우도록 하겠습니다. 그리고 이제 여기 보시면은 칼럼의 폭은 이제 400mm로 가정을 한 거죠. 칼럼 폭은 이게 이제 칼럼이면요. 칼럼 폭은 이게 폭이니까 이게 되겠죠. 여기가 400으로 가정을 한 거고. 이건 아직 모르죠. 칼럼의 깊이. 이건 아직 우리가 모릅니다. 그죠? 이건 아직 모릅니다. 이렇게. 자, 이게 이제, 그리고 철근도 아직 모르죠. 몇 개가 뭐 어떻게 들어갈지. 우리가 알 수가 없죠. 그죠? 자, 이런 것들로 가는 거예요. 자, 그래서 이제 주어진 게 말씀드렸지만은 이제 하중이 주어져야 되겠죠. 근데 하중이 PU, MU가 바로 주어졌어요. 그죠? 그냥 감사한 일이죠. 왜냐하면은 PU, MU를 모르면은 우리가 하중계수를 곱해야 되는데, 이렇게. 하중계수를 곱해야 되는데요. 1점이나 1.6이나 이렇게 곱해서 우리가 팩터드 로드를 만들어야 되는데, 그죠? 요 하중계수가 안 곱해져 있는 요 MD, ML 이런 걸 우리가 우리가 또 부르는 용어가 있습니다. 그 부르는 용어를 우리가 뭐라 부르냐면은 서비스란 말로 부릅니다. 서비스 모멘트, 서비스 사하중, 서비스 활하중 이렇게 부릅니다. 이 서비스란 말을 넣어 붙이죠. MU처럼 이렇게 하중기수가 들어가 있는 그런 용어는 우리가 factored라는 말을 붙이죠. factored. 그래서 하중에는 두 가지가 있다. 첫째, 서비스 하중이 있고 factored 하중이 있다. 이거 만일에 혼동하면은 설계 처음부터 틀려나가죠. 그래서 이거 혼동하면은 설계가 처음부터 틀려나갑니다. 절대 혼동해서는 안 되겠습니다. 그렇죠? 처음부터 틀려나갑니다. 큰일 납니다. 그래서 서비스 하중 또는 factored 하중 이렇게 나눠진다. 반드시 명심하시기 바랍니다. 그래서 우리가 다시 문제로 왔어요. 문제로 왔는데 여기서는 이제 다행히 우리가 뭐죠? PU로 되어 있는 걸 봐서 PU로 다 되어 있는 걸 봐서 이건 우리가 factored로 이해하는 게 맞습니다. factored. 그죠? So we take this as a factored actual load and factored moment and concrete compressive strength given rebar yield strength is given 30 megapascal, 420 megapascal. And the moment top and bottom are same. Moment that column receives at top and bottom are same. 이게 이제 기둥이라면요. 여기에 모멘트가 위에 걸리고 아래 걸리죠. 이렇게 모멘트가 위아래 이렇게 같이 걸린다. 같은 모멘트가 걸린다. 그런 뜻입니다. And we need to use a 25mm bar, 10mm bar for tight, and we calculate this is a nominal diameter of the bar. Okay. So, do we have all we need to start the design? Yes, I think. So, let's start design. 여기서 이제 제가 몇 스텝으로 한번 구분을 해보겠습니다. 자, 여러분 이 스텝대로 앞으로 설계를 하시면 됩니다. 앞으로 회사에 가셔도요. 첫째 스텝. We have to estimate AG. AG가 뭐죠? 그쵸? Gross area죠. Gross. 컬럼 전체의 Gross area. 전체의 면적이죠. 컬럼 전체의 면적은 우리가 지금 알 수가 없잖아요. We have to design. We have to find it. Based on these conditions. So we have to find size of columns based on these conditions. So we don't know, unfortunately. So there's a guideline, fortunately, which is given right here. This is guideline. This is guideline to calculate AG, gross area. 이게 이제 gross area를 계산한 가이드라인이에요. We know PU, we know FC, you know FY, and we don't know PT. What's PT? PT is rebar ratio. Low T, I should say low T. Rebar ratio. So rebar ratio is not unknown, isn't it? We don't know that. But we have a clue. Idea. Clue is idea. We have clue about rebar ratio. If you remember, we can assume rebar ratio based on these recommendations right there. Okay. So rebar ratio can be assumed based on this recommendation, economic for tie column sections. So 1 or 2%. We are very fortunate to know this value. So here we go and assume 0.015. 그냥 이 사이 가정한 거예요, 이렇게. If you want to assume 0.02, that's fine. So, but recommend to assume rebar ratio between these two values, so we assume 0.05 for rebar ratio. That's it. Very simple. So all we need to do is to substitute all this information in these equations, which is given for AG. So PU is given, right? PU is given this, the problem conditions, and 0.4, and FC was given 30, and FY is given 420, and low T was assumed to be 0.05, and FY is 420, and this is a FC. So FC, FY, low T, and we got everything.